Okay, welcome to chapter 9. We're into the last basically 3 lecture days of our course. And so what I'm going to be doing is kind of combining in a very quick way some material that out of both chapters 9 and chapter 10 that I would like for us to look at over the next couple lecture days. So today I'm going to be looking at section 9.1, and this is where we're going to be making inferences from two samples. Because in reality, most of the time, what you're going to be doing is you're going to be comparing two samples when you do hypothesis testing. Most of the time, you're not going to be comparing it to some number, which is what we do in chapter 8. You're going to compare it to another sample. And so it's really important to be able to go ahead and transfer what we learned in chapter 8 to this with two samples. Okay, so we're going to look at two proportions, and then the next class we're going to be combining section 9.2 and 9.3 together, just very briefly with that. And I'll kind of tell you like how we're going to streamline these so that we're not looking at it quite in the detail that we might otherwise have done if we had more time. Okay, so what we're going to do is in this section, we're actually going to look at two things: hypothesis testing, conducting a hypothesis test of a claim about two population proportions, okay? And we're going to look at constructing a confidence interval estimate of the difference between two population proportions. So an example of that, you might want to compare male and female IQs. You might look at the fatality rate of car accidents in teenagers versus senior citizens. So a lot of times we want to compare two different groups. And this is the type hypothesis testing that will allow us to do that. Okay, so some notation that you need to be familiar with. We're going to subscript everything with ones and twos. If it's coming from sample 1 or population 1, then it's going to be subscripted with ones. So P sub 1 is the population proportion for population 1. P hat sub 1 is simply the X over N for population 1. N sub 1 is the sample size for population 1. Q hat sub 1 is 1 minus P hat sub 1, or the complement to P hat sub 1. X sub 1 is the number of successes in the first sample, and we could go through and change all these to twos, and they would correspond to population number 2. Okay, so a couple things about the requirements. The two proportions are from two simple random samples. That kind of goes along with what we've been saying. The two samples are independent, and samples are independent if the sample values selected from one population are not related to or somehow matched or paired with the values from another population. Okay, so we're not looking at like a before and after for the same person. That type of thing would not be the type we're talking about here, because that would be a dependent situation. Here we're looking for independent samples. So for each of the two samples, there are at least 5 successes and at least 5 failures. So you can do the calculation here, or if you can identify what a success is, then you can, and as long as you have at least 5, then you can go ahead with that. I want to show you these formulas, not because we're going to use them, but so you appreciate what the calculator is doing for you. So our test statistic for this type of hypothesis testing looks like this. And you can see this is pretty significant, especially considering that the pooled sample proportions, which are these P's with the bars over them, you have to do a calculation for each one of those. It's a pretty involved calculation, but thankfully the calculator is going to do most of it for us. Okay, and the same thing with the confidence intervals. Our margin of error is pretty complicated here. The one thing I want to point out for the confidence interval is that if you notice here on this center part, instead of having a P, we have the difference between these. So P sub 1 minus P sub 2, that's what we're going to have put in the middle. Okay, so for our hypothesis testing about two population proportions, our null hypothesis is pretty easy. It's always going to be this, because we always assume that the two are equal, and then our alternative is going to be in some way that they don't equal each other. So it's either that population 1 is less than population 2, the proportion for those, proportion 1 is greater than proportion 2, or proportion 1 does not equal proportion 2. So it's still those same different inequalities. except instead of comparing it to a number, you just compare it to each other. Okay, so here's an example. Connecticut and New York are contiguous states, both having laws that require front and rear license plates. The proportion of Connecticut illegal cars with rear license plates only is 239 over 2,049. So we're going to let this be our x sub 1, and this is going to be our n sub 1, and this is our p hat sub 1. Because remember, p hat is x over n. Okay, the proportion of New York illegal cars with rear license plates only is 9 out of 50. So this will be our x sub 2, our n sub 2, and our p hat sub 2. Okay, so the sample percentages obviously appear different. So 11.7 and 1.6 do look to be different, but the question becomes, are they significantly different? So we know that from sampling, we get a little variation in our samples regardless of whether there's a difference or not. So the question becomes, is there a real difference? Is it significantly different for us here? Okay, so this is just a little table to kind of organize it. We've got Connecticut and New York. The ones with rear license plate only, this was our x sub 1, this was our x sub 2, and our n sub 1 and our n sub 2. And we could just find the ones that don't have that by subtracting the 2,049 minus the 239 gives us the 1810 and so forth. So we want to use a 0.05 significance level. So this is our alpha, and a p-value method to test the claim. So here's our claim that Connecticut and New York have the same proportion of cars with rear license plates only. Okay, so when we go to set this up, we've identified our claim, we've got our values and so forth. So we want to check our requirements. We're assuming it's a simple random sample. They're independent because the cars are not matched up. The ones in Connecticut are in no way connected to the ones in New York and so forth. As far as our number of successes and failures, if we look at this, these are considered our successes and these are our failures. So successes and failures, those are all greater than 5. So we're good with that part of it. Okay, so once we've identified our claim, so the claim is that Connecticut and New York have the same proportion of cars with rear license plates only, then to set this up, we know that we're comparing two proportions, so it's a two proportion type test, and we're going to let the null hypothesis be that they equal each other, which we're always going to do for this type. And since there's no indication of greater or less than, we're going to do a does not equal here for the alternative hypothesis. The good news is everything else is done on the calculator. Okay, so what we're going to do is we're going to go over to test, go to stat, and then test. We're going to go down to number 6, which is 2 proportion z-test. And so instead of calculating our test statistic, instead of calculating our p-value, we're going to get this part from the calculator. You do still have to do the null hypothesis, the alternative, your you have to write these down, the test statistic and the p-value, and then you have to draw your conclusions. Okay, so at the 2 proportion z-test, we're going to enter our x sub 1, our n sub 1, our x sub 2, and our n sub 2. Choose the tail of the graph for the alternative, so it's a does not equal, and then calculate, and you can see here's our test statistic, and here's our p-value. So we have a very, very small p-value. See this negative 12 means we would move this 12 places to the left. So I would have like 0.11019, so a very, very small p-value. Okay, so because it's so small and we compare it to 0.05, our p-value is less than our significance level. So we choose to reject the null hypothesis when that happens. So we reject this null hypothesis, and we do that in so there is sufficient evidence to warrant rejection of the claim. So this was our claim, and we said we're going to reject the null hypothesis. So there is sufficient evidence to warrant rejection of the claim that the two were equal. Okay, or there is sufficient evidence to conclude that Connecticut and New York have different proportions of cars with rear license plates only. Okay, so we would like on this example to use the sample data that we were just working with to construct a 95% confidence interval estimate of the difference between the two population proportions. Okay, so when we look at this, we're going to do all this on the calculator. So we're going to go over to test, and we're going to go down to two proportion Z interval. So we want to choose interval when we're doing a confidence interval, and we want to choose test when we're doing a hypothesis test. You should basically already have this pre-entered from the previous example. Put in your confidence level and calculate. And so here is our confidence interval that you'll see displayed on your screen. When you write it out, you actually want to put in P sub 1 minus P sub 2 because that is going to be what we're trying to estimate. That's the difference between the two proportions of the population. So looking at this, what we see is that 0 is not in this interval. So if 0 was in the interval, so if P sub 1 minus P sub 2 equaled 0, what that is saying is that P sub 1 equals P sub 2. But P sub 1 minus P sub 2 is not equal to 0. It is somewhere above 0 because of the way it's captured between these two values. So essentially what that's saying is P sub 1 does not equal P sub 2. Okay, so the confidence interval limits do not contain 0, suggesting that there is a significant difference between the two proportions. So if it did contain 0, then we would not be able to say there was a significant difference between the two proportions. All right, here's another example. The question we're examining here, do people have different spending habits depending on the type of money they have? So 89 undergraduates were randomly assigned to two groups and were given a choice of keeping the money or buying gum or mints. And the claim that we're testing is that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. Okay, so here we're going to test this claim at the 0.05 significance level. So group 1 is going to be the ones with the larger denominations, okay? And those are the ones with the $1 bill. Here, these are the ones that are given 4 quarters instead of a $1 bill. So these are going to be our smaller denominations, okay? So in the breakdown of this, we had 89 total, which means we had 46 and 43 for our ends. And of those that spent the money in group 1, there were 12, and in group 2, there were 27 of those. So when we go to set this up, we're going to, first of all, do our requirement check. And so we assume it's simple random samples. There's not really any, when we look at these, we had 12 who spent the money, 34 who did not. So our success and failures would be more than 5 for both samples. So we're good with that part of it. Okay, here the claim that money in large denominations is less likely to be spent, we can express that claim as P sub 1 is less than P sub 2, because here if we're saying the large denominations is less likely to be spent, then the large denomination, that's going to be like our group 1 or our P1 and our P2. So we want to have P sub 1 is less than P sub 2 for our alternative hypothesis. Our null hypothesis is always going to be that they're equal to each other. So when we go to put this in, we'll choose the two proportion z-test. We'll enter our x sub 1, n sub 1, or x sub 2 and our n sub 2. And this one we'll choose a less than. So we end up with a test statistic and a p-value that is 0.0002. So we still want to compare that to the alpha. So if we compare 0.0002 and the alpha of 0.05, we'll see that the p-value is less. So we're going to conclude that we reject the null hypothesis. Okay, so looking back, this would be our claim here. So we're saying that we're going to reject the null hypothesis in favor or in support of the claim. So our conclusion would be there is sufficient evidence to support the claim that people with money in large denominations are less likely to spend relative to people with money in smaller denominations. Okay, one thing is that our sample was undergraduate, so we can't always generalize that to the general population because undergraduates may do things different than the general population would. Okay, our next example, we want to construct a 90% confidence interval estimate of the difference between the two population proportions. and then answer the question, what does the result suggest about our claim about people spending large denominations relative to spending small denominations? Okay, with this, we're going to choose our 2 proportion Z interval since it's a confidence interval. We've got our X1, N1, X2, N2, and we said 90% confidence interval, so we'll put in 0.9, and we get this as our confidence interval. So we have those 2 endpoints with P1 minus P2 in the middle, and we notice here again, 0 is not in our interval. Okay, so basically what that tells me is that P1 does not equal P2 because of the 0 not being within this. So the confidence interval limits do not include 0, implying that there is a significant difference between the 2 proportions. So the 2 proportions are not equal to each other. There is a significant difference between the 2. So there does appear to be sufficient evidence to support the claim that the large denominations is less likely to be spent relative to an equivalent amount in smaller denominations. Okay, a couple things in the directions on MyStatLab. Your directions may say choose an appropriate confidence interval estimate. So in order for your confidence interval to test the same thing that your hypothesis test is testing, we have to adapt our confidence level in certain ways. If it's a two-tailed test and you're given an alpha, then you're just going to do 1 minus that alpha, and that's going to give you the appropriate confidence interval estimate. So like if alpha is 0.05, 1 minus 0.05 is 0.95, and therefore you'd have a 95% confidence interval that you would be testing. If it's a one-tailed test, we actually have to double the alpha. So if for a one-tailed test, if alpha is 0.05, then we're going to double that and subtract that from 1. So 0.05 is actually going to give us a 90% confidence interval. Here, if you've got 0.01 and it's two-tailed, then 1 minus 0.01 would be 0.99, and that gives me a 99% confidence interval. A one-tailed test is going to be 1 minus 2 times 0.01, which would be 0.98, so I'd have a 98% confidence interval. So just keep in mind when it's telling you to choose an appropriate confidence interval estimate that the one-tailed test you're going to need to make this adaptation for. Okay, here's an example that I would like for you to try. So go through, test the appropriate claim, construct the appropriate confidence interval, and then see if you can answer the question that follows. All right, so we've got a study that investigated survival rates for in-hospital patients who suffered cardiac arrest. Among 58,593 patients who had cardiac arrest during the day, 11,604 survived and were discharged. Among this number of patients who suffered cardiac arrest at night, this number survived and were discharged. We want to use a 0.01 significance level to test the claim that the survival rates are the same for day and night. Okay, so if we set this up, we're going to let X sub 1 be 11,604 and N sub 1 would be 58,593. X sub 2 would be 4139 and N sub 2 would be 28,155, and we have an alpha of 0.01. So we do need to set up our null and our alternative hypothesis. So if I do this, I'm going to have P1 equals P2, and we're testing the claim that the rates are the same, so there's no indication. So it would be does not equal. So this is going to be my claim statement here. So when I go to put this in the calculator, I'm going to enter it like this with the does not equal. So I'm going to get this test statistic and this p-value, which is basically 0. So if I compare 0 plus to the alpha, and my alpha was 0.01, the p-value is less than the alpha, so we're going to choose to reject the null hypothesis. Okay, if I go back here, I'm going to reject the null hypothesis, which is my claim. So I'm going to say there is sufficient evidence to warrant rejection of the claim that the survival rates are the same for day and night. Okay, moving on to our confidence interval. This one we were asked to find, we're using a 0.01 and it's a two-tailed test. So if I look at this and I put this in, I'm going to do 2 proportion Z interval, and I get this this interval here, and I would use a 0.99. My alpha was 0.01, but since it's a two-tailed test, then that's going to correspond with 99% confidence interval. So I'll put the P1 minus P2 in the middle. 0 is not in here, so basically there is a difference between day and night. I would like to look at this problem using StatCrunch just to show you how you can do some of these with StatCrunch. So if we go to Stat and go down to Proportion Stats, this time we're going to choose 2 sample. And since we've been given the summary statistics on this one instead of the actual data, we're going to choose with summary. Okay, so that's going to ask us for our number of successes. So our X sub 1 was 11,604. And the number of observations was 58,593. And then for the second one, it was 41,39 and 28,155. And we had said it was a two-tailed test on that one. So with the two-tailed test, we can compute, and you can see here that our test statistic is 18.26, which is what we had found, and our p-value is less than 0.0001. It's not going to specify as small of a p-value as what we found. It's just going to kind of quantify it by saying it's less than 0.0001, and usually that's small enough to be able to make the same conclusion. Okay, if we wanted to do the confidence interval, what we would do for that is go back to Stat, Proportions, 2 sample with summary, and instead of choosing hypothesis test, we're going to choose confidence interval. So we'll put the same information in, except here for our confidence level, our alpha was 0.01, so we're going to want a 0.99 confidence level. Compute that, and we see that we have our lower limit is 0.044, which is what we had, and 0.058, which is also what we had for that. So you can do this on your StatCrunch as well if you are starting. So I think some people are actually starting to enjoy StatCrunch, and so if you're one of those, then you can do it on StatCrunch instead of the calculator. All right, here's another example for you to try. So try setting this one up and answering these questions. Okay, here's our claim. We're going to test the claim that the incidence of malaria is lower for infants using bed nets. So let's organize this, and we're going to say that we have bed nets and those that did not use bed nets. So it's really important to keep organized which one's going to be population 1 and which one's going to be population 2. So here we'll have x1 is 15, n sub 1, I'm getting ahead of myself. N sub 1 is 343. So x sub 2 is 27 and n sub 2 is 294. Alpha is 0.01, and we want to test this claim. So when we put it in the calculator, we'll do our 2 proportion Z test, enter our data values, and we need to set up our null and our alternative hypothesis. So we'll have P1 equals P2. And then for this one, claim that the incidence of malaria is lower for the infants using bed nets. So bed nets is population 1, and those that do not use is population 2. So this is going to be a less than. So when we go to put it in our calculator, we're going to use the less than symbol. So here we get our p-value. If I compare that to my alpha of 0.01, it's less than that, so I'm going to reject the null hypothesis. Okay, looking back at this was my claim statement here. So if I reject the null hypothesis in favor or in support of this claim statement, then I'm going to say that there is sufficient evidence to support the claim that incidence of malaria is lower for infants using bed nets. Okay, so test the claim by constructing an appropriate confidence interval. This particular one was a one-tailed test, and our alpha was 0.01. So what we're going to do is we're going to do 1 minus 2 times the alpha. So that's going to give us 0.98. So that's my confidence level here. And I've got my values, and I'll calculate, and I'll get this. So here, 0 is not between these two values again. And so therefore, we do see a difference between the two. So it's only including negative values, which indicates that it is lower. In order to have negative values, if we've got P1 minus P2, if that's going to be negative, then P1 has to be less than P2. So it's basically saying the same thing. And do the bed nets appear to be effective? They do appear to be effective because the rate of malaria is lower for infants who use the bed nets. Okay, so that takes us to the end of section 9.1. I hope we gained a little bit of an understanding about how to use hypothesis tests to compare the two populations. Just keep in mind that we are not going to be doing major calculations for test statistics and p-values. We're going to just be totally relying on the calculator to do those for us, but you still need to show me the steps for your null hypothesis. You need to write down your test statistic and write down your p-value, write down your conclusions, and then you'll have everything I'm asking for on that. Okay, thank you and have a good day.